Hello. Good morning, everyone. Welcome to another episode of Sa Talk Show. Today, I'm going to talk about geometric inversion. Geometric inversion, that is what it is. Let me show you some pretty graphics, okay? Open that, and let's see, open that. Geometric inversion, open that, and open that. Okay, so let me show you. Okay, so geometric inversion, we're gonna talk about that, and the stereographic projection, which is a video we did a week ago. So this is the stereographic projection, and we are going to derive their formulas. So what is the formula for stereographic projection, and what is the formula for So this is stereographic projection, and what is the formula for geometric inversion? So this is what you are looking at. You see, grid becomes that. You know, this bunch of rectangles, squares becomes that, and becomes that. You know, depending on whether the center of the square is in the middle or not. So this is also geometric inversion, two-dimensional case. And this is also two-dimensional case, but we made it into a three-dimensional tiles. We added a thickness, so it becomes beautiful like that. Can be used for garden decoration. So if you have a house, you have a garden, you want tiles, you can do this. But then, you know, we did a video talk of this one, live coding. So you see the squares in the middle become smaller, infinitely smaller. So you don't want that when you want tiles in a garden. So you do some geometric transformation. You apply a function to the 2D plane. So you get rid of the tiny, infinitely small squares. So you get that. And you can do, again, you can make it a tile, 3 tiles. So this is beautiful. Okay, we did a video of this. And then you have 3D. This is a three-dimensional geometric inversion. You know, you have a bunch of cubes evenly spaced in a space. You know, then you do a inversion, then you becomes that. Okay, you can rotate it. So here's the code. Yeah, let's run some code. Okay. So let's see if we can do that. Let's start Wolfram language. So we're gonna explain geometric inversion, stereographic projection. Yeah, then I'm gonna show you what is the relationship between. Actually, there's more fantastic, beautiful geometric inversion. So this is a nested inversion of a bunch of circles. So you begin with these 7 circles arranged in a hexagonal way. Then you invert each circle with respect to each one of them. Then you do it again, then you do it again. I believe 4 times, then you get these spectacular graphics. So all these are geometric inversion, okay? So in this one, and this one, and this can be used for gate, you know, iron gate. You have if you have a house, you have gates in front, right? You know, usually rich people's house have a gate in front, and they have like curlicues decoration. So you can use that as a pattern. You know, iron rods, curlicues, you know, for the gate decoration, or floors, you know. And so all these are geometric inversion. You start with a pattern on the left, a grid, it becomes that. And if you start with a bunch of parallel lines arranging a pentagonal way, symmetry, rotational pentagonal symmetry, 5-fold rotation, then you get this figure on the right. So, but if you have a hexagonal kind of a star grid, then you get this picture. And if you have a colored squares like that, then you get this picture on the right. So all these are geometric inversion. Very fantastic. Okay, so this is 2D case, and like we explained, we can do it 3D case. Okay, so all these are geometric inversion, and here's a definition I'm going to go over. And also this spider web kind of thing, beautiful, fantastic. That's also geometric inversion. And then we're gonna explain how it relates to stereographic projection. They are related mathematically. And also we are going to derive each of their formulas, okay? Then we are going to code Wolfram language. We're gonna code a spectacular graphics. I hope so. I hope this video is gonna be 1 hour, and I hope I have good enough time to do that. If you have comments, questions, post it, okay? The streams, am I doing okay? The stream's current bit rate is lower than the recommended bit rate. What the? Okay, so it looks like it's okay now. So geometric inversion. So let's do it. So first of all, I want to, let's see what we want to do. So today's talk show is here. I'm using Emacs and Starfly keys. So here's the source code, HTML page. And here's what we're going to talk about. So we showed a bunch of graphics. And I'm going to show you the definition. Okay, let's start with definition. Okay, geometric inversion. So very easy. Okay, so you can just go to my website. Let me show you which page that is. Yeah, so this page. So this page, you just search for XRD, a visual dictionary of spatial plane curves. I did this like 20 years ago. And then you just go to inversion, geometric inversion, then you'll see. So here's a definition. Okay, you start by, let me see if, let me show you this. Okay, yeah, so let's use GeoGebra. Okay, GeoGebra is a kind of free application on the web you can use to build this, to draw this dynamic graphics. So inversion, okay, geometric inversion is a transformation of the plane. Let's stick with the 2D case. So you have a plane, you are given a circle, okay, of radius r, okay, and it's a transformation, meaning any point, given point on the plane, you're gonna change the position of the point to somewhere else, okay, for every point. So there's a function. So for each point, the function takes 1 point, two numbers, coordinate x and y, and it returns another 2 numbers, another point, x and y. So given any point, it returns another point. This is called a transformation, or in geometry you call this transformation, or you can just call it a function. Okay, so given a point, it moves the point somewhere else. So how does that work? So you given a circle, usually a circle of radius 1. So here's a point P, and it returns the point Q. Okay, Q is the return value. Okay, so how does it work? Is that you draw a line from the center of the circle to the point, to the given point. So there's a line, and this line will pass, it will intersect the circle. Then you take the distance from the center of the circle, let's call that O for origin, okay? Center of the circle to the point P, the distance. And the new point is a point on the line, on this OP line, such that the distance OP times the distance to the OQ is equals to the radius squared. Okay, so do you see what I mean? So let me draw that. Okay, so hold on a second. Let me draw that. So let's start to make okay, so let's draw this. Let's see if we can do that. So given let's see. Yeah. Okay, I cannot. I need to go here. Yeah. So okay, so now wait. That snip and sketch. Okay, so given the distance O, okay, OP, the distance OP times the distance OQ is equals to r squared. R is the radius of the circle. So if you want to know the So you can manipulate this formula. So OQ equals to R squared divided by OP, okay? That's the line, the distance, okay? So the distance O2Q is equals to the radius divided by O2P. So let me go back to the GeoGebra to show you how this transformation works. So you can see as the P moves further away, Q becomes, the point Q gets closer to the circle. If the P is near the is on the circle, then Q is also on the circle. If P goes inside the circle, then Q goes outside. You see, so this transformation basically swaps all points outside of the circle into inside, and any point inside the circle becomes go to outside. So you can see there is some kind of symmetry of the P and Q point. You see, the further away is P, the closer is Q to the center. The closer is OP, then the further is OQ. So that's so this is kind of like a mirror. So like if you have a mirror, the right side becomes the left side goes to the right side. If you have a L, it becomes L like that on the other side. So in a similar way, but the line of the mirroring is not a straight line, it's a circle. So anything outside gets reflected. You can kind of say it get reflected to the inside, and inside swapped to the outside. So it's fascinating. So this is a definition of geometric inversion, okay? And okay, so that's a definition. So let's and with this definition, there are certain very interesting properties. So remember, we begin with a point and we get a new point, and then we can prove that a line, if you are given a line in the plane and you do the geometric inversion for every point of the line with respect to a given circle, then of course, if the line lies outside of the circle, then the new points will all be inside of the circle, and they will become a circle. So a line becomes a circle. This is one of the property. You can prove it. And a circle will also become a circle. So let me show you, okay? So let me see. So here is an inversion of lines. You see these vertical lines, they become these red circles. And if you have circles like that, the blue circles, horizontal, with respect to this yellow circle, this inversion circle, then they become the red circles like that. Circle will become circles, and lines will become circles too. So in fact, you can consider a line is just a special case of a circle. When the circle gets infinitely large, it becomes a line. You can think of it that way. Just as you think of the reflection, reflection is a line where the left side becomes the right side, like the symmetry of a human. But with inversion, it's like reflection, but everything get inverted inside and outside. So you can think of this circle, when the circle becomes larger and larger and larger, the circumference becomes flatter and flatter. And if you take the limit to infinity, it becomes a line. It becomes the normal reflection. So you can think of it that way. Okay, so let me show you some of the. So here's the animation. So you can see how it works. The inversion of a circle becomes another circle. So let's do it. Let's do it a line first. So here is the line, the blue line, and the red is the image of the line. So you see, given any line, you can move the line anywhere. So with respect to inversion to this circle, let's move this to the center, okay? So with respect to this yellow circle. I don't know if you can see that. The yellow circle is the inversion circle. So this blue line becomes this red circle. So if we move the line, watch when it touches the circumference. So you see, a line becomes a circle, and when the line crosses origin, it becomes a line again. So you see, so here you can kind of see the how lines become circles. You can consider that a line is just a degenerate circle. A line is a special case of a circle when the radius becomes infinitely large. You see, now you have a small circle, now it gets larger, 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 and infinitely large. It becomes a line. So it's very interesting. So anyway, the point here is a line becomes a circle of lines. Okay. Now let's try. Let's see another case with a circle. And you can prove all that. There's proof here. You can read them later. So let's show a circle case. Where is it? Oh, here. And no, not here. Yeah, here. So here is a case of a circle. So we have a circle here. If the circle is further away, you can see the red circle is its image. So circles become circle. Okay, so that's the geometric inversion. And here you can also see how it becomes a line. A circle becomes a straight line. And it got swapped to the other side. So anyway, again, any point outside of the inversion circle gets mapped to the inside. You can see P and Q there. Here is P. So this point gets inverted over there, and this blue circle gets inverted into the red circle. And we can move the circle about, so you can, let's see, enlarge the circle. So again, the blue circle is outside, it becomes inside. And let's shrink it a bit, okay? So if we move the circle, cross it, and if we move it inside, you can see how it goes to the outside. And you can see here is when a circle becomes a line and swap to the other side. You can see. Very interesting, okay? So geometric inversion. So that's how all these graphics are. So, in this case, you begin with a colored grid like that, and you do the inversion, and it becomes like that. And here is a mechanism. Let me show you this way. This one. So this one is, in the 1800 or so. This is called Poisselier linkage, something like that. Basically, it's a mechanism to turn. It's a linkage. It's a mechanism called linkage that essentially demonstrates based on the geometric inversion principle. So you can see this is a mechanism. You just got a bunch of bars fixed on a point, on a pivot, or however you call that. So if you move this point on this line, this linkage forces the 2 points such that one is the inversion of the other. So this is useful when you have robotics. For example, the legs of a dog, you want to control, you have a motor that can only go, roundabout, but you want the legs to move, back and forth. So this is one of the, there's all sort of linkages that does that. So this is one of the earliest to turn a circular motion into a rectilinear motion. The the math principle behind it is inversion. Okay. So that's, and there's more. There's another famous linkage called Hart's linkage. I don't have a interactive demo of that. And let's show you something interesting. Okay, so here is a geometric inversion of a sine curve. So this blue thing is a sine curve. So you can see the P point moves, and the red curve is its inversion. So you can see, and the green is the given circle to invert. So again, any point outside of the circle goes through inside. You see Q is here, and when the point P reaches the circle, its image is the same. P and Q are the same. Then when the point is inside, it goes outside. So you can also move the, let's see if we can move the, yeah, so we can move the, you see? Now the blue line is the, sine curve. So now it's outside of the circle. So the image becomes very small inside the circle. See? Very interesting. Okay, so now we want to derive the formula. Okay, so hello immortality. Everything good? Say something, guys. This bitrate problem. Okay, so let's see. So we demonstrated geometric inversion. What do we do next? Let's see. So I want to Archimedes spiral. So here is another interesting one. Let me show you that one. Okay, so you are looking at this spiral. This spiral is called Archimedean spiral. It's a family of spirals. So there's not just only one of them. There's like multiple of them of one parameter. So you can see this animation shows you different Archimedes spirals. And this animation, there's more. So all these are Archimedes spirals. Archimedes spiral is defined by this polar equation. Radius equals to angle raised to the power of n. So given a number n, let's say n equals to 1, then you have radius equals to theta. So that means as theta, so this is polar equation. Theta just turn around, okay? Theta just go around. So theta, basically, this means when r equals to theta, that means when theta turns, the radius is proportional to theta, okay? So it's a kind of proportional, you get a proportional spiral. So as when you have more theta, you have more distance from the center, the radius. Okay, so you can see that's a result. R equals to theta. Now, but if you add power to theta, theta equals raised to 2 second power or third power, then you get other things. You get other kind of spirals. Okay, so that's Archimedes spiral. So let's show you. So there's a GeoGebra. So at this rate, I don't think we can start to code. Okay. So anyway, so this is Archimedes spiral. You can drag this to change the n to see different spirals. So all these are Archimedean spiral. So when is n equals to 1? Okay, this is when n equals to 1, okay? So let me show you. So you see, this is this Archimedes spiral. So when the power is 1, you have the formula r equals to theta. And this specific spiral is called Archimedes spiral. Now, when the power is not 1, Then you have other spirals that's called Archimedean spiral. Okay, so it's hard to see. Let's see. You see that? So it's a family of spirals. So when the power is negative, then you got things like this. Then it becomes like that. Okay, and you often see these as you often see that as anyway. Never mind. Okay, so there are many different spirals. They are used in architecture, in decoration, and so on. Okay, so that's Archimedes spiral, but what about the inversion? So let's show the inversion of this spiral. So somewhere here. Okay, so the blue line is the Archimedes spiral. Okay, so let's make it 1, and the red line is its inversion. This green is the inversion circle. Okay, so you can see you have different Archimedean spirals, and the red is its inversion. And basically, Archimedean spiral inverts to itself. An Archimedean spiral, its inversion is again Archimedean spiral. So you can kind of see the blue curve and the red are Archimedean spirals. Okay. So so that's about some of the fancy. We are showing some of the fancy graphics of the inversion. So just to get a sense of what it looks like. I love my Emacs tutorial. Okay, thank you. Today is not Emacs. So now what we do next? Oh yeah, so let's run some of the code. So let me just show you. So we did this in past video. Let's start Wolfram language. So next, I want to derive the formula, but so here is Wolfram language code. I want to derive the formula, but that's gonna be another half an hour. And I was planning to do coding it, coding a fancy graphics. These are old, we did last time, so I'm just running it so I can show you. So here is a geometric inversion of a bunch of squares, and this one 3D tile, very interesting. Let's copy it. Here's a code. Copy it, paste it here, run it, and okay, so let's make this pretty so you can see rendered math formulas, and that's a source code. So you get this thing. Let's run it again. So you get this thing. You begin with this image, then you do a geometric inversion, then you get this. Okay, then you add z-axis, you make it 3-dimensional, so you get this. Then you just add thickness to it, then you get that. Okay, so that's the graphics we did last time, and I just want to show them again. Run it. Oh, I don't want traditional form. Run it. Okay, so this is a bunch of cubes and inverted geometric inversion in 3D. So can we show the cubes? Now let's not do it. Okay. Okay, I wonder if there are something basic about visualization questions like the distance between a point and a straight line. Distance between a point and a straight line. Yeah, you are. Yeah, you can do that. But let's move on with what we're gonna do today. Okay. So let's see what we wanna do next. We want to derive the geometric inversion formula. Okay, so how do we do that? And we want to show the relations between geometric inversion and stereographic projection. Okay, so if you don't know, stereographic projection is just like that. So let me show you their relationship. Okay, so let's start paint. Okay, so let's see if we can do this. So given a line, given a circle, so in stereographic projection, this is a 3D case, but you can also do it on 2D. So this here is a 2D case. So this is X, and this is Y. So what you do is that you project the line, given a point X, given a point on X, this point is P. So you draw a line from the center of the circle to P. Then this line, this should be a line straight. Okay, so how do you erase things? Yeah, this is not good. So anyway, so you draw a line passing the point P and passing the center of the circle. Then you will have this new point, and this point is called Q. This point is called Q. So this point Q is a stereographic projection of the point P in a two-dimensional case. So any point P on the x-axis, it corresponds to a point on the circle Q. Okay, so this is kind of a two-dimensional case. So you can do it in 3 dimensions, and the same principle applies. So that's how we get that. Okay, we did a video last time on this, and you can see, given a image like that, you have the result like that on the right side. And you can also demonstrate this by shining a light onto a ball. The light must be at the north point of the circle. Then the shadow automatically becomes their projected point. Okay, so this mathematician, friend Henry Sedgman, he did a video, fantastic. Okay, so you go watch that video. So anyway, and there are other interesting. So this is very useful in math. It's used in complex analysis. So anyway, so we have the stereographic projection. So how does this relate to inversion? Okay, so let me explain. So here is the stereographic projection. This is not good. So let's do. So if you have, so what is the relation between stereographic projection and geometric inversion? Okay, so let's do it again. Let's do the graph again. So here is the x-axis, here is the y-axis, and suppose you have a sphere here. Okay, so given a point P on the x-axis, you draw a line through it, and here this point is Q. Okay, so this is stereographic projection by definition. Any point, on a circle, you project the line. Wait, actually we did it wrong. Shit. It should be from the North Pole, not from the center of the circle. Okay, but so there should be a line like that. So, and this point is called Q. So that's a stereographic projection. Now, how does it relate to inversion? So now imagine there's a circle twice as large. So the circle goes like that. So here is the center. Okay, so this large circle, now you are going to do, so before, given a point P, we want to find the stereographic projection of the point P. So you just draw a line from the North Pole to P, and the intersection with the circle is your image, the result of P. Okay, so any point P will have a point Q on the circle, on the stereographic projection circle, the small circle. Now you can do this without using stereographic projection to get the point Q. Okay, how do you do that? You can do that with geometric inversion. So you just imagine a bigger circle twice as large. So what you do now is you invert the point P with respect to the inversion circle. Then you can see you get a point Q, and this point Q will be exactly the same as the stereographic projection. So you can see any point on this line X, and when you do inversion, remember a line inverts to a circle, to this small circle. So when you do inversion with respect to the large circle, and since it becomes a circle, because a line becomes a circle, and since this line is outside of the circle, so any point on the line goes inside the circle, and any point touching the circle will not change. So you can see this line, x-axis, becomes exactly the stereographic projection circle. Okay, so that's their relation. So that means when you try to code this image, normally we use we try to find the intersection of the line and the circle to determine the point. But now you have a different method. Instead of trying to find the intersection, you can just compute the distance of the North Pole to P, times the North Pole to Q will equals to twice the radius of your stereographic projection. So you can find that point. So you don't have to do the intersection anymore. So that's a different technique. So let me show you Wikipedia. Wikipedia has a good explanation. Okay, so let's see inversion. Okay. So here is the inversion. So they explain inversive geometry, and you can see this beautiful animation. That's fantastic. That's inverting a Mandelbrot set, some sort of Mandelbrot set, inversion of lambda Mandelbrot set. Okay. Okay, and now let's go, and they explain the same way I did, and there's many interesting properties. And circle become lines, And here is how they explain the relationship between stereographic projection, with respect to the green circle, can be equivalent, is actually equal to the inversion of a circle twice as large. So this point becomes that point, that point becomes that point. So two ways to do it. Okay, so that's the mathematics of it. So next we're going to do. So there are a few things we can do now. One is to derive the formula for stereographic projection. Okay, we're gonna try to derive the formula for that. For this projection, and also we can try to derive the formula for geometric inversion. That is, given a point in the plane xy, you want to find the formula that gives you the result point, the coordinate. So we can derive those formulas. Then the other thing to do is to actually code it in Wolfram language. Okay, so what do we do first? Let's see. So here is inversion. So here is the stereographic projection and inversion. So how do you derive the formula? That's I haven't been doing this for a long time, so let's see. Basically all you need is trigonometry. Okay, you don't actually need to solve any equations, I don't think. But how do you do it? Oh my god, I forgot. So basically, given a circle, this small circle, and given a point P, you want to find the coordinate of Q. And how do you do that without using equations? You can solve it by using an equation of a circle and equation of a line. So you have equation of a line is two variables. Equation of a circle is also two variables. So once you have that, you have two equations with two variables. So you can find the Q, their intersection point. You have two in this case. So that's one way to derive the formula of stereographic projection. But is there another way without using equations? For example, let me show you. Okay, so for example, let's cheat. Okay, let's use Wolfram language to solve the equation. But anyway, it'll explain. So a circle is x squared plus y squared equals to r squared. Okay, so this is how you do equation in Wolfram language. Okay, so and you can make it look nice. So that's a formula for a circle centered on the origin. Okay, so we can plot it. Contour plot. Okay, Let's see if it works. Okay, you need 3 arguments are expected. Oh, so you need xy minimum. Okay, so Wolfram language needs to know which one are the variables. So x is a variable, and you want to plot it from -2 to 2, okay? And y is also the variable, and from -2 to 2, okay? Let's do it. Okay, so then you want to say, oh, it doesn't know what is r, so you have to set a value for r. In this case, let's say r equals to 1. Okay, so you got a circle of radius 1. Now we want a line. Now now this circle is centered on the origin, 0, 0. We don't want that. We want a circle centered above the origin. We want the small circle. Okay, so again, we are trying to find the formula for the stereographic projection. So we want a circle centered above. So in order to find that formula, we can just so this is a basic analytic geometry. If you remember, you can just say x minus 1, okay? And replace y by y minus 1. I think so. Let's try it. Okay, yeah, so it worked. We should not move x, so x should be x, y minus 1, okay? So there. So we got a circle now centered on 0, 1. Okay, and that's not, so now we need to work this out. So we want to know, we need to decide on what is the radius we're gonna use. So let's use 1. So this is radius 1. Yeah, okay, that's already radius 1, right? So that's the formula for a circle. Now what about the formula for a line? Okay, I don't remember my my analytic geometry since 30 years ago. So but we can easily do it just by trial and error. So an equation of the line is going to be, let's just start over, okay? So equation of the line is going to be y equals to something x. Okay, so yeah, you need to know the slope. Okay, the slope is, so we want to find this one. Okay, yeah, okay. In order to know the line, you need to know the point P first. God. So P is going to be a variable. So so let's suppose P is a point such that P equals to AB. Okay, AB is some constant. So basically, we want to find a line. We want to find an equation of the line that passes the North Pole, that pass this point, which is 0, 2. Okay, that's one of the point it passes, and it will pass another point, which is AB. Okay, now we don't know what is AB, but I mean, we assume it's some constant. So we want a formula that represents a line that passes through these 2 points. Okay. Now I don't remember my calculus, but this is an easy case. We can actually just derive it. Okay, with basic understanding of vectors. So the point P is 2 coordinates, A and B. In fact, B is 0, because remember, we want the point P is always on the x-axis. So P equals to A0. Okay, so we just have one variable. Okay, so we want the equation of the line that passes these 2 points. Very easy. Okay, very easy. So now in general, the equation of the line is y equals to mx. Okay, m is some slope, right? So that's the equation of the line. It's a linear equation because there is no powers involved. So let me do, yeah, so that's correct. Okay, so that's a linear equation. This is a general form of equation of the line, and now you just want to find in terms of a. So you basically have, well, God, this is back to linear algebra. So what we have is P equals to A0. A is X. So we have y equals to ma. Okay, that's the first case for the point P. Then the other case is for the point 0, 2. Okay, so let's do that. So y is 2. So we have 2 equals to mx. M, and what is x? X is 0. So m0. So that's just 2 equals to m. Okay. So now we got 2 equals to m. Then we know y equals to 2a. So that is this is our formula for a line that passes 0, 2 and passes any of the a. Yeah, so that is our formula. 2 equals to 2a. Let's write it. Let's say it again. Y equals to 2a. So y equals to 2a. So this is so now a is a variable. Let's just say a. So let's plot that. There it is. We got the line. But it looks like this line is incorrect. Did we get it correct? Okay, so I'm not sure where are we going. So this is incorrect. I have to think about this a lot. So right now this is incorrect. So because this line passes the point 0, 0, wait, what are we doing? So we want the line that passes these. Oh yeah, so we got mixed up. So if you want the line that passes, okay, so we need to actually write a lot more formulas. I don't think I can do it. Well, I mean, I cannot do it in 5 minutes. It'll take some time. So we are trying to find the formula. Well, the general formula is, okay, we can just trial and errors, okay? The general formula is just that, okay? So it's just that. So this allows you to see. So let's say 1/2. Okay, and yeah, so this is, yeah, oh, I forgot. We need to add, you need to move the line up. So there's a constant, we forgot the constant. Let's add 2, okay? So 0, yeah, so here we have a line that passes the point 0, 2. So here is 0 and here's 2. That's what we want. We want the line that passes the north pole of the circle. Yeah, and now this number is just the slope. Okay, so this number, we can define m equals to, let's say, 2. Okay, so let's copy that. Let's put it here. Okay, so this number can be 1.5. Okay, so, and if it's 1, let's say 10, -10. Yeah, okay, that's good. That's likely. So now let's do this. Manipulate that expression with m goes to 0, 3 to 3 instead of 0.1, okay? Okay, so now we got a animation, interactive animation. So you can see, so all these are lines of an equation that passes through the north pole. So let's play it. Yeah, so this is exactly, that is our equation. That is our equation of the line. So now we have two equations, okay? One equation is this one. Equation of the line with a given m, okay? M is, you know, whatever point we want, you know, that's why it's variable. And the other equation is the equation of a circle here, this one. Yeah, that one. So we have two equations, these two, okay? And we want to solve it, okay? We can solve it, we can try to solve it by substitution. You know, y equals to that, then you just replace this y by that, you know, replace this y by this, and then you got an equation of one variable x. Then we solve, you know, we can do this by hand, but it's quite tedious to write here. I have to create another, yeah. You know, so we got the equation x squared x squared plus mx plus 2 minus 1 squared equals to 1. Okay, so now we simplify this. This mx 2 minus 1 is mx plus 1 squared, and you have to multiply them out. Then you basically got a quadratic equation, okay, like x raised to the power of 2. Then you try to solve for x. But let's try just use the Wolfram language to solve it. Okay, let's see if this works. Solve. Attempts to solve the system expression of equations or inequalities. Okay, yeah, we can use that. So solve that, and we want to solve for x. Try it. What? Empty. Okay, domain. Oh, okay, so you have to, the syntax is incorrect. Instead of the list, you have to say and. So that's one equation, and the other equation, solve for x. What? Clear M. Let's try this out. Examples. Let's try XY. Okay, now it's better. Yeah, so you can see here x0, y2 is one solution, and here is the other solution. This is the part we want. Exactly. Now, yeah, exactly. Now, what is M? M is just our A here. Yeah. So actually, yes. So now we have a formula we derived ourselves that given a point P on the x-axis, we can find the point Q. And the point P is two numbers. So how do you work this out? So point P is basically just M, okay? So point P has two coordinates, x and y. And the y coordinate is always 0. So you can think of the point P is just M or some transformation, but you know, basically point P would be M. So given M, you have a new point x exactly. Yeah, so that looks correct because I've worked with this, you know, many times before in the past 20 years. This formula is correct. So for example, let's extract okay, so now we have this let's define it as solution, okay? Solution equals to that, okay? So now, let's, you know, when the P is at origin, which means M is 0, X is 0, the result point should be 0, 0 as well. So when m is 0, let's replace m by 0. Okay, so when m is 0, we get this, it gets the other point. So there's something that needs to be fixed. Let's say when m is 1, let's see what happens. X equals to -1, y equals to 1. X equals to -1. Okay, the formula is not correct. Okay, I think that's it for today. We we failed. I didn't do any preparation. So, we tried to derive the formula of the projection formula in 2D. This is really simple, I haven't done it for a long time. So we are trying to derive it. That's a key here. But there are many ways. You can also look. There are so many ways to derive it. Right now we are trying to use linear equations, multiple linear equations of a circle and the equation of the line. We can also do it with a vector. You just wait. Can you actually derive the formula by using vectors? You probably need some geometric theorems about classic Asian geometry. Yeah, I don't know. So let's look up Wikipedia, and I'm gonna shut down in a minute. Yeah, I'm gonna shut down. Wikipedia. So we want stereographic projection. I have to go. I'm kind of tired sitting for too long. So here's the stereographic projection. You can see they give you the formulas. They show you how to derive it. It's so simple that you don't even, there's not much derivation, but you do have to be familiar with the basic analytic geometry. Yeah, it's so now I'm trying to say, well, actually I gotta go, guys. So terrible. This is a terrible video. I gotta go. My wife is calling me. Bye, guys.